Lazy LLM is an efficient inference technique. This technique, in particular, is useful for long context scenarios. Let me explain. In this paper, they are discussing optimizing the inference process of transformer based large language models like Llama, and there are various others. The inference process consists of two stages. An inference means whenever you ask a question from LLM. First stage is pre-filling stage. This stage computes the KV cache for prompts and generates the first token. Now what is KV cache? KV cache refers to the cache of key value pairs used in transformer based LLMs. In the pre-filling stage, the model computes the KV cache for each token in the prompt. The KV cache contains key and value. Key represents the input token, value represents the corresponding token embedding. The KV cache is used to compute the attention weights and context vectors for each token. Now, let's take one more step back. Let's start with transformer based models. These models are a type of neural network architecture introduced in the paper Attention is All You Need in 2017. They are primarily designed for natural language processing tasks such as machine translation, question answering, and text generation. The transformer architecture is based on self-attention mechanism that allows the model to attend to different parts of the input sequence simultaneously and weigh their importance. This is different from traditional recurrent neural networks or RNNs, which process the input sequence sequentially and have recurrence connections that allow them to capture long range dependencies. Transformer based models consist of an encoder and a decoder. The encoder takes in a sequence of tokens such as words or characters and outputs a continuous representation of input sequence. The decoder then generates the output sequence and one token at a time based on the encoder's output. This is where KV cache comes in. The KV cache is a data structure used to store the intermediate results of the self-attention mechanism. It's a cache of key value pairs that are computed during this encoding and decoding process. Keys represents the input token and are used to compute the attention weights, whereas values represent the corresponding token embeddings and are used to compute the context vector. The KV cache is used to store the pre-computed key value pairs for each token in the input sequence. This allows the model to efficiently compute the attention weights and context vectors for each token without having to recompute them from scratch. So now we know what is transformer based model, what is KV cache. Now let's look at this paper again. What this paper is suggesting here is that this method, lazy LLM, is to optimize the inference process of transformer based large language models. The main idea is to selectively compute the KV cache only for the tokens that are important for the next token prediction. That's it. Instead of computing it for all tokens in the input sequence. If you look at this diagram, this is prompt based LLM inference, which can be divided into two sequential stages. First stage, pre-filling and decoding. For long prompts, the first token generation during pre-filling stage could be slow. As an example, for Llama to 7 billion on average, the time to generate the first token requires 21 times the wall time of each subsequent decoding step and accounts for 23% of the total generation time in the long benchmark. So if you look at this diagram, this gives you another side of it. So this is a comparison between standard LLM and lazy LLM. Instead of computing the KV cache of all input tokens at the pre-filling stage, lazy LLM only selectively computes the tokens that are important to the next token prediction, deferring the computation of remaining tokens to later steps. Lazy LLM significantly optimizes TTFT by reducing the amount of computation during pre-filling. Also, as some tokens in the prompt are never selected by lazy LLM during the whole generation process, Lazy LLM also reduces the amount of computation and accelerates the overall generation, and that is what this is all about. So all in all, really good stuff, I would say, because this new technique could really save a lot of costs there, because it selectively computes the KV or key value cache for tokens important for the next token prediction, and lazily defers the computation of remaining tokens to later step when they become relevant. They have also examined lazy LLM on various tasks, and they have observed that the proposed method effectively reduces TTFT with negligible performance loss. It is also worth noting that their method can be seamlessly integrated with existing transformer based LLMs to improve their inference speed without requiring any fine tuning. So I'm eagerly awaiting the code to be released, and as soon as they do it, I'm going to make another video and I'm going to show you how actually it works in practice. I will meanwhile just drop the link to this paper in video's description. Let me know what do you think. If you like the content, please consider subscribing to the channel. If you're already subscribed, please share it among your network as it helps a lot. Thanks for watching.